Welcome to the next video, that is Introduction to PN Junction. I am Annie P. Joseph, Associate Professor in the Department of Electronics and Communication from Jyoti Engineering College, Cherudurthi. In the last video, we have learned how you form a P and an N-type material. So I'm just giving you a pictorial diagram of it. You can look into this. So the left side shows that this is a P-type material, and in the P-type material we have the circles which are known as the holes, which are nothing but the missing of an electron. So the trivalent atom introduced into the parent silicon or germanium atom will have one missing on the covalent bond as having space to fill an electron. So that is called as a missing of an electron. So that is the hole that we call that. And since this impurity atom is ready to accept an electron, we call that as the acceptor ion, which is given by the blue circle with a negative sign. Coming back to the N-type material, which is formed by the introduction of pentavalent impurity atom to the parent atom. So the 4 of the pentavalent form covalent bond with the 4 silicon atom, and one of them is free to form a covalent bond. So they form the free electron, which is the dark circle, which is indicated by the black dots, which is called as the free electron. Now this impurity atom is capable of donating this free electron to the conduction band for conduction. That is why we write that as the donor ion with the plus in the circle. That is, so N-type material, when we write an N-type material, we write them with electrons and the donor ions as represented here, whereas in a P-type material we write the holes with a circle and an acceptor ion, which is negatively charged. That is, the concept is it can accept an electron, so we write that as negative. Here in N-type material, it is capable of donating an electron, so it becomes a donor ion. The independent P and N-type material cannot be used in many places. The applications are very few. But whereas if the P and the N-type material are fused together, then the applications are larger in number. So then they form a PN junction. That is how. So the formation of PN junctions are of various technologies. You just can't bring it together and form them. It has got various processes wherein which you have to fuse them with various temperature and form the PN junction. That's why I've written various fabrication techniques are used to form a PN junction. So now looking back here, the terminal P. So the P, you take out a terminal from the P and that will become the anode, and the terminal connected from the N becomes the cathode. So PN junction. So we will discuss what is this depletion region later. Now the important property of a diode is its ability to conduct in one direction. Hence it's called as an unidirectional device. So how it is going to conduct in one direction will be explained later. The symbol of the diode is shown in the figure 2. So this is how your symbol of the diode is represented, figure 2. Now here in figure 1, so the arrowhead in figure 2, when you look, you have an arrow here. So this arrowhead will become the anode, and the line which is here will represent the cathode. Now look at this block here. You have a P and an N. The direction of the current is indicated by the arrow which is shown here. So the direction of current flow is from P to N as in figure 1, and it is from this arrow, or it's from this direction of the flow of current the symbol of the diode came into existence. Now the applications of PN junction diode, it's used as a rectifier, it's used as switch. Some of the applications are mentioned here. Now when a P and an N junction is formed, the P region has holes and negatively charged impurity ions called as acceptor ions, and the N region has free electrons and positively charged impurity ions called the donor ions, which we have already discussed. Holes and electrons are the charge carriers, while ions are the immobile one. There are minority carriers which are thermally produced. Now a P and an N junction is formed, and you have holes, electrons, donor ions, acceptor ions in the P and the N type material. Now when these is fused together to form a PN junction, what happens is at room temperature the covalent bond breaks without any external voltage applied. The thermally produced charge carriers will always be present there. So the more of covalent bonds are broken, when the temperature increases, the electrons and holes are released, and that will constitute your minority carriers. So this is how a P and an N junction is formed. In the earlier slide I represented the independent P and N type. Now the P and N are fused together, and this is how it will happen. You have the donor ion, the acceptor ion, the free electrons and the holes. Now as soon as a PN junction is formed, this is what is going to happen. Now this is without applying any external voltage. Electrons near the junction from N side diffuse to reach the P, where they combine with holes. Now because of which the N material loses an electron and will have a positive charge, and this happens only near the junction. We look back to the diagram here. So the electrons which are in the N type will cross the junction and come and occupy here near the junction. It's only near the junction that's happening. So when this electron is lost completely from this N, so what happens? They become negatively charged here. So what happens? Near the junction you have a negative charge. Remember in the last video I had told you that this N type and the P type independently, when you take, they are electrically neutral, because it's not missing an electron or gaining an electron completely. It is present as a whole. So only when you take out an electron from this complete N type, you get a negative charge. Unless and otherwise, if it's not taken, you don't get that as a negative charge. So that is why this N and P type are neutral. But now when a P and N junction are fused together, these electrons near the junction will have a tendency to move towards the cross the junction and move to the P type, because they have a missing of electron. So this N type will have a positive charge. At the same time, the P junction in the P type near the junction will have a positive charge, because it has acquired an electron from the N type. So due to which N material losing an electron will have a positive charge, and this will happen only near the junction. At the same time, the P material gaining an electron will have a negative charge, and again this happens only near the junction. The region near the junction contains only immobile ions and devoid of free carriers, and is called as a depletion region. So earlier I told you what this depletion region is. So here what will happen in P type near the junction, you will have negative charges, and in the N type you will have positive charges. So N and P. So these are free of charge carriers. You have ions there. So they have called as a depletion region, devoid of charge carriers. That's why it's called as a depletion region. Barrier potential or space charge potential. The depletion region contains immobile ions which are electrically charged. These ions will have an electric field which opposes further diffusion of charge carriers. So going back again to the diagram, I told you you have the P type with the negative and N type with positive. So negative and positive, you have a small amount of electric field. So this electric field will have a potential, and that is called as a barrier potential or space charge potential. So the electric field creates a potential difference across the junction, which is called the barrier potential or space charge potential, which is 0.3 volt for germanium and 0.7 volt for silicon. That is, if the parent atom that we have taken for P type is germanium, it will have a barrier potential of 0.3 volt, and if it is silicon, it will have 0.7 volt. Now look at this. This is the depletion region that is formed. Okay, so without any external voltage given here, you have a negative charge near the P junction, and in the N-type you have a positive charge. So now here you have a electric potential. So it is something like a fictitious battery here. So this is like a battery with negative here and with a positive, which has got a voltage of 0.7 or 0.3 depending upon the material that you use for formation. So in a PN junction, without any external voltage, a barrier voltage is developed across the junction and no current flows the junction. Working of a PN junction diagram. For any semiconductor device to operate, an external voltage is to be applied. So the external voltage that you apply will be called as biasing. So you define biasing like this, that is, applying proper DC voltage is known as biasing. There are two types of biasing. The one is called as a forward biasing and the other one is the reverse biasing. So we come to forward biasing. When positive terminal of the battery is connected to anode and negative terminal to the cathode, the diode is said to be forward biased. Look at this. So this P, this is connected to positive, and this is negative, which is connected to N. So this is how you have a forward biasing. This is the diagram where you have not given any bias. You just have a depletion region of 0.7 volt. We will take silicon as the standard one, and we discuss with silicon every time now. So you have 0.7 with no bias given. So this is the bias which switched on. What is going to happen? We have to look into that now. So this is what happens. I have given a bias here with a voltage. Now when my bias voltage is 0, there is no flow of current. Why? Because this potential which is there is already 0.7 volt. So 0.7 is greater than the voltage that you have applied. So there is no flow of current. Gradually, as we increase this bias voltage and it becomes greater than the barrier potential, this junction is broken. It's something like a tug of war where the barrier potential and the bias voltages are comparing. When your bias voltage becomes greater than the barrier potential, that is completely broken off. Then you will have the flow of electrons and their results in the flow of current in a PN junction. So now this is what is going to happen. So I'll just read this. When a PN junction is forward biased, holes are repelled from the, that is missing of electrons from the positive terminals towards the junction, are repelled from the positive terminal and move towards the junction. Similarly, electrons are repelled from the negative terminal of the battery. So look back to the diagram here. So what happens here is, so here you have missing of electron. So this missing of an electron will have a tendency to move forward, whereas now here when you look into this concept here, the N type is made up of electrons, and these electrons will repel from the negative terminal of the battery or the source. So what happens is they move across this, they repel and they cross, junction is already broken. So these electrons will move towards the junction and then move to the P and then come out. Now how is this current going to flow? The concept is explained in as follows. Now when an electron leaves the negative terminal of the battery, as soon as it is switched on, the barrier potential is broken, the electron will leave the negative terminal of the battery. So now as soon as an electron leaves the negative terminal of the battery, because of the positive potential at P, in P type the covalent bonds are broken. So you will have an electron and a hole pair broken. So what happened? This electron is the one which is going to come out from P type and reach the positive terminal. So this is what So how do you define current? Current is nothing but a flow of electron in a closed path. So how does this current come in the device? So you as soon as this bias is switched on, electron will leave the negative terminal of the battery, enter into the n-type, and at the same time the positive potential of the battery will make the breaking of the covalent bond where electron and hole pairs are broken and an electron will be released. So you will have this electron coming out from P to complete its path, giving rise to current. So when once the potential is barrier is broken, these electrons are free. So the electrons will leave the battery, covalent bond is also breaking, and then it will result in the flow of current. As a result, more majority charge carriers diffuse across the junction and large current flows through the PN junction. Magnitude of the current depends on the applied voltage. So energy from the external source increases and becomes greater than the potential barrier. Junction barrier is broken. Now, what is reverse biasing? When negative terminal of the battery is connected to the anode and positive terminal to the cathode, the diode is said to be reverse bias. The bias diagram is shown here. This is what is going to happen now. As soon as the bias, there will be a depletion potential barrier of 0.7 volt. A bias is being given now. So electron is leaving the negative terminal of the battery. So electron will come in. Now here what happens? Here electron is left here. It comes and occupies into the p-type. So you have more of electrons there. So already near the junction you have p-type. So this electron also reaches into the p-type. So more of electrons are accumulating in p. Similarly at this n-type, the covalent bonds are broken because of the positive potential. So you have more electron hole pair. Electrons can leave this and come to the positive terminal of the battery. Positive terminal of the battery. So you have positive charge. So what is happening? The width of the depletion region is increasing here. Once again I repeat, electrons leave the negative terminal of the battery to enter the P. In n-type, covalent bonds are broken because of the positive potential. So the electrons that are there will be attracted by the positive potential. So you have positive charge here. So negative positive charge. The amount of the accumulation of charges are getting more and more. Therefore the width of the depletion region increases. And when once the depletion region width increases, there is no flow of electron to come out from the P through the external circuit. Therefore the flow of current in reverse bias condition is less. So I just repeat that when a PN junction is reverse biased, holes in P type are attracted towards the negative terminal of the source and electrons are attracted towards the positive terminal of the source. See, now this is just a conventional matter that we write here, but this is what is actually happening in a reverse bias condition. Holes get attracted, missing electrons in P type are attracted to the negative terminal of the battery of the source and electrons are attracted to it. So this is the way that we when you write in the note material or when you write it, this is what is available in the text. But this is actually the concept is this. What I explained, electron move from the negative terminal of the battery to enter the P. Because of the positive potential connected to n-type, the covalent bond in n-type break, giving the electron hole pair combination. Electrons in n-type will get attracted to the positive terminal of the battery. So you will have negative charge in p-type and positive charge in n-type. So the depletion width is increasing. So this widens the depletion region and increases the barrier potential. The increased barrier potential prevents the diffusion of majority charge carriers because of this barrier potential. So the barrier potential is becoming equal to the bias potential now. So what happens? The electrons are not able to cross this junction and come out of the p-type to the external circuit. So there is no flow of current. Thus there is no current in a reverse bias PN junction due to majority charge carriers. The junction offers high resistance under reverse bias. This is the concept of reverse bias that we have discussed. Thank you.